Hello everyone, myself I am Sai. Today I'll be presenting Auratylix, a social video intelligence platform developed as part of this assignment. The objective of this project was to build a system that can analyze social media content beyond basic engagement metrics and provide meaningful insights through natural language interaction. To achieve this, the Auratylix was designed to compare content across YouTube and Instagram, analyze transcript level information, generate actionable recommendations, use retrieval efficiently only when additional information is required. Well, the overall problem statement was provided as part of this assignment. My focus was on designing and implementing a solution that is reliable, scalable, and capable of handling real world challenges while delivering accurate, grounded responses. Let's talk about the architecture overview. The system is organized in two independent pipelines, an extraction pipeline and a conversational analysis pipeline. First, the extraction pipeline is further divided into two pipelines. The first one is YouTube oriented, and the second one is Instagram oriented. And the conversational analysis pipeline is responsible for intent detection, retrieval orchestration, and response generation. One of the key architectural decisions was to completely separate content extraction from conversational analysis. This improves modularity, simplifies debugging, and enables independent scaling of components. When thousands of users uses the same pipeline again and again, this helps us to prevent the breaking of the pipeline and prevents the load on the back end. A few engineering decisions I took to improve this project was I'll discuss about suggestions first. While the assignment mentions that the model should be able to provide suggestions, while we cannot directly rely on random LLM answers and suggestions and lose our customer to LLM hallucination, I ingested few data in the vector DB taken from few verified sources to provide suggestions for YouTube and Instagram, which provides a fact-based backing to the answers rather than the random LLM answers. And one of the strongest engineering decision is what we call session first RAG architecture. Most systems do take user query as input, does retrieval and generates answer using LLM. And but we here what we do here is different. We take user query as input, but we go first for session context and then retrieval only if needed, which follows like tool-based reasoning instead of integrating RAG directly into the pipeline. This significantly reduces the latency, retrieval cost, and vector DB load. This is where difference between basic RAG systems and production RAG systems comes. And another important decision is intent-aware retrieval. An LLM classifier determines the query intent, whether retrieval is required or not, which collection should be queried. We maintain two separate collections. First one is knowledge base for recommendations and strategy, and the second one is social content for transcripts and extracted content. This prevents retrieval contamination and improves retrieval quality. And I also implemented few fallbacks for the reliability purpose. And social media platforms are generally unreliable. The APIs may fail, the captions may disappear, the access methods may change. So we designed a fallback pipeline. Like suppose for YouTube, you can see in the figure, the primary API is YouTube transcript API, but the fallback is YTDLP audio extraction followed by growth for transcription. And for Instagram, metadata is extracted first. Transcription is generated only when deeper analysis is required. This approach reduces compute cost while still maintaining reliability. The system gracefully degrades instead of failing completely. Now let's see the application in action. I have pasted two URLs. The inputs can be different, like it can be YouTube URLs or two Instagram URLs, or it can be cross-platform, like one YouTube and one Instagram. So let's click on analysis. The extraction pipeline starts. Uh, inside the process, metadata will be collected, transcript will be generated, relevant semantic content is embedded and stored in ChromaDB, and a session will be created. Now, you can see, the cards have been shown adjacent, and you can see the full metrics. These are the full metrics: views, likes, comments extracted from the respective URL. You can see the full metrics here. These are real-time metrics and no preset metrics. You can see the transcript extracted here, and you can see the video engagement rate. And yeah, the session has been created. The session is active. The respective ID is shown. And yeah, we can start asking questions here. Like suppose I have asked a question like find audience. The response will be generated based on true facts. Like we have pre-ingested the data, we have the session data. You can see the answer has been given. The assignment also asks the questions like comparison of you can see the comparison has been done, respective hooks has been done, the conclusion has been provided. Like even you can see well, you can see the responses have been presented in such a way that it feels like we are using an enhanced UI. No, when I ask a question that triggers an recommendation mode, the system retrieves supporting context from the knowledge base collection and combines it with extracted video information. Like this demonstrates how different query types follow different reasoning paths. Well, I want to show you another feature which is often missing from projects is observability. Uh, in this project, I have implemented LangSmith tracing. So every execution is traced through LangSmith. Here we can inspect prompt execution, tool usage, retrieval faults, latency, cost, and failure points. So let me show you one simple example. You can see. So when I have pressed on analyze, you can see the system has basically triggered the extract video hook, and then it extracted the video. Like I have implemented a fallback. So if the transcript API fails, it will be going to the Grok whisper to extract the video. So you can see it stored the video documents in the RAR. So this happens every time we implement something and the tracing has been done. So instead of guessing why a response was generated, we can inspect the entire reasoning path. This makes debugging optimization significantly easier, and we can also estimate the exact cost it's going to be in the production, and how the optimization can be done. So, one of the major problem in general implementations is at 10,000 users, uh, one of the most expected bottleneck is in-memory system storage. So what I use is disk-based temporary storage instead of in-memory buffers for fallbacks and for API transcripts. So when captions are missing or blocked, Whisper transaction requires temporary audio storage, and using in-memory buffers or bytes IO works for a single request, but fails under concurrency. But when with thousands of users at the same time, it creates thousands of audio files in the RAM, which makes the server to be crashed. So what I implemented is temporary directory for the for the fallbacks and the for main implementation. So even if 1,000 audio files are stored on disk, RAM stays low, deleted, the audios will be deleted later as it's a temporary disk. I'll conclude here. I hope you liked it, and I hope I hear a response from you. Thank you.